is finding the force on a wall, on a dam or a window or whatever. So the one concept that we mentioned last time that I just want to mention again is that when you have a dam, all that matters is the water that's right next to it. It doesn't matter if there's 1 mile of water or 2 miles of water behind it. Hydrostatic pressure is sort of canceling each other out because water is pushing in all directions simultaneously. So if you have 1 foot of water against that dam or 1,000 feet, it's the same cumulative force on that dam. All right, they call that the hydrostatic pressure. We're finding the cumulative hydrostatic pressure. And we all know that the deeper you go down, the more pressure increases. Right? And we're sort of summing all those pressures up at all the levels to get the cumulative hydrostatic pressure on the dam. And we're going to use the same acronym that we used before. So getting to know like when you look at this, it looks really crazy, and that sort of feels very difficult to memorize. This is going to be our acronym, and this works super well for the problems that we already did when we were finding work. The same acronym with one modification for finding force. All right, so remember that when we found work, we were doing ADD multiplied by volume. If we take away 1 unit of length, we are at area instead of volume. And if we take away a unit of length from work, we get force, because work is force times distance. All right, so if you take away 1 unit of distance, then we're back to force. So the acronyms work great. The ADD means the same thing, acceleration, density, depth, or distance. And when we're thinking about being submerged, ADD turns into pressure. The units of ADD, if you were to look at the units of acceleration, density, depth, that's pressure. That will have units of pressure. And then ADD times area gives you force, because pressure is force per unit area. And if you multiply by area, the areas disappear and you're left with pressure. So I've got a bunch of explanations down here, a bunch of unit things that you can look at just to convince yourself or to try to kind of get a handle on the units and how they all tie together. Let's go through the mechanics of doing one of these. So this right here is the ADD. So there's ADD. And then the width across the dam, that has units of length. dy has units of length. So this is an area right there. So that's how we're going to memorize this. ADD area. So when we're in this 2-dimensional case, we use area. When we're in the 3-dimensional case, when we're finding work, we use volume in the parentheses. Once again, remember that I'm trying to cue you that with the parentheses, it's not just the area of the dam, it's the area of a strip. Just like with the work problems, the volume in parentheses isn't the volume of the vessel, it's the volume of a cross-sectional slice, cross-section with thickness. So here we go. So we've got water pushing on this dam. The small base is 10, the big base is 15, and we want to know the cumulative pressure. So the first thing that we're going to do is start out with our formula, ADD area. And the area, again, is the area of that red horizontal strip. So the area that we're looking at is just the area of this red horizontal strip, and then we integrate it as that red horizontal strip moves throughout the region. So the area of that red strip is the width across times dy. dy is the height, if you will. It's the thickness of that red strip. So when we see that area down here, that area means the area of the red. So W times dy. So all we have to do is find W to find that area. All right. So when we look at this, for this particular example, we've got 20 across the top. We've got 10 across the bottom. If we are going to find this distance right here from there to there, we have two choices. We can find the equation of the left edge, the equation of the right edge, isolate x because we're finding a horizontal distance, and then do right x minus left x. We could also acknowledge that there's some symmetry here, that if we put a vertical axis right there, put a coordinate system right there, we could find this distance right there from this function and then double it. That's also an option. So instead of finding both equations of those tilted edges, we could find just the right edge. So let's go ahead and do that. Let's find the equation of that line right there. To do that, it's probably easiest to label these points. Many of you can probably start to see the equation really quickly. It's very easy to make a mistake finding these lines because it's easy to sort of, not divide by 2 when you're supposed to. So the coordinates of this point are 5, 0. The coordinates of this point are 10, 0. So if you write down those points, it's going to be a little bit of a hedge to not accidentally make a mistake when you're finding the equation of the line. This line does not go through the origin, so we can't, it's not as simple as that cone one we did on Tuesday, where the edge had slope, whatever the slope was, y equaled mx was the equation because the y-intercept was 0. So we have a little bit more work. So typically what I recommend is using the point slope formula. So y minus y1 is equal to the slope times x minus x1, where y1 is the y-coordinate of a point, x1 is the x-coordinate of a point that's on the line. Yeah?
Would the top guy be 10, 15, or is it 10, 0?
It is not 10, 0. Thank you. Thank you, thank you. So they tell us that the height is 15. Thank you very much. We would have seen real quick that the line here does not have slope of 0, because we would have done y minus y, and it would not have worked out. Okay, so thank you. Does it matter which of the 2 points we pick? Of course not. Pick either one. I'll pick that one because there is a 0 in there for a coordinate, so that'll make it a little bit easier. So it's going to be y minus 0 equals the slope times x minus 5. So I've applied that point, x1, y1. The slope is the change in y over the change in x. So from this point, we're going up 15. And we're going over how far? Going over 5. So up 15 over 5. So that tells us that our equation is 3 times x minus 5. We mentioned a moment ago that we need to isolate x because we're solving for a horizontal distance. So we have to isolate the x. So let's come over here, and we have y equals 3x minus 15. So we're going to have 3x equals y plus 15. And then we finally divide by 3, and we get a third y plus 5. So that is measuring this purple distance right here. So if we want W all the way across, so therefore W is going to be 2. Maybe I won't distribute the 2. It might not be that beneficial to distribute the 2. So we have that. That's our W. And that's probably the hardest part of the problem, is getting the W. So look at that. If you have a question on how any of those steps come to pass, ask. So this 2 is by symmetry here. That 2 is a symmetry 2. All right, so now we're good to go. Yeah?
When you isolate the x, that final step, shouldn't it be 1/3 y plus 1/3 5? Or
So I divided by 3
oh,
here.
wait, never mind. I
see it?
Yeah,
15 divided by the
15.
3 is how we got the 5. So yeah, the 3 does distribute.
yeah, okay.
Yep, for sure. Okay, so now our cumulative force is the integral. This dam or window, whatever it is 15 meters tall. So we're gonna integrate the pressure at each level from 0 to 15. So ADD is pressure, A is acceleration due to gravity, so 9.8. D is the density of the fluid that's pushing against the wall, which again is 1,000 for water. Beer would have a different density. The second D, this is the one that's got a variable in it. So the first two are always constant. AD is always constant. Depth, we want to know how far down we are, so we're trying to figure out this distance right here. Very similar to the problems that we already did earlier. What's that distance?
15 minus y.
15 minus y. So this generic strip that I drew here is the generic horizontal strip at y. Just like a generic rectangle that's vertical is at x, a generic horizontal rectangle is at y. And that complementary distance, this is 15 all the way to the top. This is y right to there, so that complementary distance is 15 minus y. So that goes in right there. So there's the ADD. That's pressure. So if you multiplied all those together, you'd have units of pressure. Okay, pascals, units of pressure. Now we have to do the area. And again, area is not the area of the whole dam. It's the area of just the red strip, which is the width of the red strip. There is the width of the red strip multiplied by dy. So this is area right here. That is area right there. And then this part is pressure, which is ADD. Pressure is ADD. Acceleration, density, depth. So there's our setup. Ask if you have a question on any of these steps. So we're going to factor everything out. Once again, we get that 9,800. Looks like we're going to factor out the 2 also. I'll just multiply them together. There might be some arithmetic that we need to do to figure some things out. So the only stuff that's left are these 2 parenthetical quantities. We'll FOIL those, get a polynomial, and integrate. So when we FOIL these, we'll have negative y times that, so that will be negative 1/3 y squared. We are going to have negative 5y when we distribute to the second one. When we distribute to the 15 to the first term, we're actually going to get plus 5y. And the 15 distributed to that constant is going to give us 75. So there we go. There's our polynomial that we can integrate pretty easily. We can wipe out these 2. Those cancel. We will do our integration. I'll leave the 9,800 times 2 here for a moment. Maybe there's going to be some cancellation. So this will be minus 1/9 y cubed. Add 1, divide by the new exponent. Here we'll get a 75 times y. And then our limits of integration, 0 to 15. So the 0 to 15, the 0 doesn't give us any force. Plug in 0, we get 0. So we only have to concern ourselves with the 15. So minus 15 cubed, whatever that happens to be, we'll get to it in a second, plus 15 times 75. So that'll be where we're at. And I wasn't able to log on to Desmos, so anyone that's got a calculator, maybe plug that in for us and tell us what we end up with for our force. And when this is a problem that has units, so we have to make sure we put units. What would be our final units here?
Newtons.
Newtons, because we're finding force. Finding force, so we'll have newtons. Whatever that all multiplies that to. Anyone have a fraction yet?
15 over 392.
15 over 392? That seems too little. 15 divided by?
I got
Oh, here.
14,700,000.
Okay, that's what I just got.
14,700,000? Is that what you ended up with? We have 2 people that got that? Okay, 3, okay, so that's gotta be it. So double check your number there. Did you get that?
Yeah.
Okay, good. Yeah, entering these things into your calculators with all the parentheses can sometimes be more challenging than it should be. Okay, any questions on any of those steps? So we really have just an extension of what we did with the lifting problems. It's just that we have ADD area instead of ADD volume. That acronym is amazingly simple to get us these semi-complex answers. Try a triangle. Oh, something fishy is happening here. There's definitely something fishy going on. Oh. Is this a problem? I already logged on once. Yeah, I'll just assume I'm supposed to say yes. I can't bother reading all that. Is my image now going to show in OneNote? Seems unlikely, right? Is that what I just did? Let's see if I click resync now. All right, that's an easy triangle to draw. It will show up. Does anyone have that triangle? Oh yeah, you got it right there. I might sneak a peek. So we have a triangular window or dam, whatever it happens to be, and we want to find the hydrostatic force on it. So let's see. I'm going to have to look at that for 1 second. How far across? It's 20 by 30. So we have 20 across the top, and the height of it is 30. So this distance right here is 30. So there's our setup. Once again, it might be advantageous to put a coordinate system here. So I'm just going to imagine that coordinate system right there. Once again, we're going to have to get the equation of that edge. This one is super easy because it goes right through the origin. When we have a line through the origin, the equation is just y equals mx. So if we were going to put a point right up here and label that point, that would be 10, 30. And the equation of this line, let's put it over here, is going to be y equals 3x. And if we isolate x, we'll get x is equal to y divided by 3. And we're isolating x because we want to know that distance across here, this is going to be the w at a random y. That's at an arbitrary height or depth, however you want to think of it. So what does w equal then if x is y over 3? W will be what? 2y over 3, right? Because we're going to double it. So we found this half distance right there. Like when we isolate x, X is going to measure horizontally from the y-axis. So it's only measuring half that W. So we double it to get W. And now we have everything we need to slot into our ADD area formula. So we come down, our force is going to be the integral from 0 all the way up to 30. And then acceleration, density, and now depth. Depth means the distance down to your strip. That's our second D for depth. 30 minus y is going to be that depth. 30 minus 30. 30 is the height.
It's kind of trippy.
I know. It's very easy to grab the wrong number. The 20 is measuring that horizontal distance across the top base. Or I guess the triangle only has one base. So there's ADD. So acceleration, density, depth. If you combine those three together, you're getting the pressure. And pressure is force per unit area. So this is force per unit area. Now we multiply by area. Those areas, the units at least, will cancel, so we'll be left with units of force, which is what we want. So we put in our width, which is 2y thirds. We put in the dy. This is the area that we are talking about in our formula right there. That is our area. Width times dy. Okay. So remember that dy has a dimension to it. It's got units of length, so it's adding a dimension. So the triangle, not too bad. So we're going to end up with the 9800 out in front. We're going to get a 2/3 out in front. And let's see what we're left with in terms of variables in the integral. So the only stuff that's remaining, we've got the 30 minus y, and we've got that y. Those are the only two things I didn't factor out. Those are the only two parts that aren't constant. So we're going to combine those. We'll get 30 times y minus y to the 2 dy. There we go. We'll integrate. 9800 times 2/3 times 15y squared. Add 1, divide by 2. And then minus 1/3 y cubed. Add 1, divide by 3. 0 to 30. Once again, that lower limit's not going to add any force to this. That's going to be a 0. So we only have the 30 to contend with. So we'll end up with a string of multiplication. 15 times 900 minus 1/3 times 30 cubed. So 3 times 3 times 3. Oh, we've got some cancellation here. Maybe I'll write this as 30 times 900 and try to do a little arithmetic. So I'll take two of the 30s, multiply them together to get the 900. And then I'm going to put the 130 here so I can cancel out that. If I was doing this by hand, I see, oh, 900 is common, so I'm going to factor that out. So we'll have 9800 multiplied by 2/3, multiplied by 900, multiplied by 15 minus 10. 30 divided by 3 is 10. The 900s are gone. They factored to the front, so we have 15 minus 10, which is 5. So that's what we have to multiply together. So somebody start typing that into your calculator while I'm simplifying this. I would put that in there and get 300. So then we have 9800 times 30,000 times 3,000. 2 times 5 is 10. Oh, we're almost able to do this by hand. 100 times 3 is 300, but then we have to subtract off 6, so 294. Maybe we can get all the way through it. Somebody confirm. Is that right? Okay, all right, we did it. All right, so
29,400,000. Yeah.
yep, 29,400,000 what? Newtons. That's a lot of newtons. It's like that. Well, it's I don't know if you guys are paying attention to that dam they're building up at Gross Reservoir outside up north west of Boulder. It's like the biggest public works project I think in the history of Colorado. They're taking the dam that's up there right now, holding back Gross Reservoir, which is the water source for Denver, part of the water source for Denver. And they're extending the dam 130 feet vertically, increasing the body of water so that it's going to be this massive body of water.
Is that reservoir that's out west of Boulder?
Yeah.
Okay.
Yeah, it's right up Clear Creek Canyon. If you go up Clear Creek Canyon on Highway 72,
Yeah, I've been
it's
by there.
it's totally insane.
I
They
used-
already had one tragedy where some guy drowned in the truck. The truck fell in the water and the guy drowned. If you go on YouTube, like some of these building projects are so cool. If you go on YouTube and look, there's a slight documentary on it, and it's fascinating what they're doing to make this happen.
I know there have been floods from problems with that dam before.
Yeah.
Before I lived in Colorado, it was years ago. But one of my friends told me about it. He was in Boulder at the time, and when he was a kid, yeah, everything was flooded.
Yeah, and in 2013 we had that flood, and the water came over it too.
They let me paddleboard up there while they were doing blasting.
Yeah.
Yeah.
Yeah. Yeah, if you come in from from the north side of it.
Sure.
Yeah, they don't let you come in from Coal Creek anymore.
Yeah, everything else is closed.
Yeah. Yeah, it's pretty cool. The other project they're doing right now, which I think is super cool, is the I-70 Floyd Hill over to Idaho Springs, that 8 mile. If you haven't looked up the project that they're doing there, it's pretty cool. They're stacking the highways. That the highway going west is going to be 100 feet high off the ground. Yeah, it's pretty cool looking. It's a lot of engineering, a lot of cool stuff.
Statics.
Statics. Okay, any question on any part of the steps here? So the big thing is this horizontal. We just have to get in our mind, how we find horizontal distances. Find the left and right curve and take the difference, or find one curve and double it. All right, that's kind of the crux part of it. Let's do the circle, the semicircle. So here we've got a pool. We've got a circular window in the pool. The pool is 4 meters deep, and I'm asking you just to do the setup here. So same context as before. We're going to look at a representative horizontal strip. Pressure is constant on a horizontal strip. And we're going to need the full width of that horizontal strip. So this horizontal strip does go all the way across, and we're going to have to find W. But if we find the equation of the full circle, isolate x, we'd have a plus or minus a square root. The positive square root would be the right edge. The negative square root would be the left edge. We could just take the positive square root and double it to get the full horizontal width of that strip. So this circle, this window, has a radius of 1 meter. The equation of a circle centered at 0, 1 of radius 1 meter, the x-coordinate is 0, the y-coordinate is 1, so we have to shift the y by subtracting 1, and then the radius squared is 1 on the other side. So now I'm just doing what I said. Let's isolate the x and choose the positive square root. This will be the right half of the circle. So that'll give us the equation of the full right half right there. So it's measuring from the y-axis to the right. So there's the x. Now I'm just doubling it to get w. Right, that x is only measuring halfway across. That red curve is the right half. This x value measures from the y-axis over. So we're just going to double it to get the actual width of the strip. And again, that's the crux. Finding the width for all of these force problems, that's always the crux of the problem. And then it's mostly arithmetic after that. So then our force is going to be 80d area. So we're going to have the integral. We're looking at all these horizontal strips throughout this window here. So we're going to go from what to what in terms of our limits of integration? So down 0 to 2. That circle has a 2 diameter. So 0 to 2. And then acceleration due to gravity, 9.8. The density of water is 1,000 kilograms per meter cubed. So there's AD. And now, the second D is always this complementary distance that we've seen. So this strip right there, your representative strip right there, how deep is it? 4 minus y. Right? 0 is down here, so that strip is y units up. If 4 is the whole distance, we take away y, we'll get that depth. So 4 minus y. So in the problems that we were doing on Tuesday, that would be the distance that something is being pumped. But you find it the same exact way. It's just the upper minus the lower. So 4 minus y, that's a second D in our formula. So now we have ADD done. That's pressure. ADD is pressure. Force per unit area. Now we have to put area here. Area is the width of the strip times the thickness of the strip, which really boils down to just the width because dy is automatic. So we found our width right here. So there's 2 times the square root of negative y squared plus 2y, and then dy. So there is the area of the strip. And if we pull out our constants, we'll get that 9,800. We get a multiplication by 2. This kind of leads us to actually what we talked about last time. I'm not going to pull the 2 out. There's a little clever observation here. If that 2 gets distributed in here, it will be advantageous. So there's our integral. The only real technique you have is substitution. And if you're going to do substitution, like we did on Tuesday, you're going to let u be this. And on Tuesday, we did a problem where the derivative of that matched right here. This doesn't quite match. The derivative is negative 2y plus 2, but we have a negative 2y plus 8. So that's our setup, though. That's what the problem asks us to do. And then I've got a little clue down here that you can, so I give you a step. I'm not going to go through it, but you can do it. The answer is right there. And here is the clever step right there. We know the derivative in here is negative 2y plus 2, which matches what I have here in red. So what you're going to do is create 2 separate integrals. You're going to distribute the square root to this quantity, the 2 minus 2y, and you're going to distribute it to the 6. And you'll see something fascinating if you go through the math there. And that will be the answer. But we'll just do the setup in here. And if you are motivated to go try to sharpen your integration skills, do that next couple of steps. All right, any questions on our setup there? Any piece of that you want to
My question,
unpack?
where did we get the 4 from the 4 minus y?
So the 4 is the depth of the whole pool. So the whole pool is filled with water.
Cool.
So we've got 4 meters deep of water if we went to the bottom.
Okay.
So y is measuring up this far. So then that distance right there is going to be the total minus the y.
And wait, is it draining out of that circle?
No draining.
Okay.
It's 2 dimensions, not 3 dimensions, so we're just finding the force on the wall, force on the window.
Okay.
So this is a window down in the pool. So if you're a parent, you're on the outside, probably looking through the window at your kids swimming around. It's like an aquarium where they just have a window looking in at the scary things. Japanese man o' wars or sharks. Everyone see the 4 minus y? So that is our second D, so ADD area. Okay, so again, remember, worksheets are due tonight by midnight, which really means tomorrow morning, because I won't lock them until I wake up tomorrow morning. And test is a week from today. So Tuesday, we'll spend the whole day reviewing. And the rest of today, we're just going to finish up our last section, 7.3. We're only doing one section in 7.3. And that one section that we're doing, we're going to zoom in just on a very particular part of Chapter 7, Section 3. So it's not a very big section. But it does entail some memorization, as most math does, if you want to be good at it. So let's go to Chapter 7. We're going to talk about the hyperbolic functions. You are super familiar with the circular functions. The circular functions are also known as the trig functions. And they come from a circle. X squared plus y squared equals 1. The hyperbolic functions, so the circular functions come from this unit circle. The hyperbolic functions are going to come from a unit hyperbola. So hyperbola has 2 branches to it, but the hyperbolic functions are defined from that right branch of the unit hyperbola. All right. Now, there's a lot of parallels here, and so this is just a very abstract parallel. You do not need to memorize this. This is just sort of a justification for some of the terminology and sort of why they are, kind of why we use the same terminology, C cosine compared to hyperbolic cosine, so COS versus COSH, cosine versus cosh. There's no standard for the pronunciation of these hyperbolics. Some people will say cosh, some people will say cosh. And then the reciprocal functions, there's all sorts of weird names for. But we'll talk about the way I learned them and the way I'll refer to them. So one observation with the unit circle. Let's suppose that we have a generic circle first. So I just have it labeled as R. Then we're going to plug in a 1 for it to be a unit circle. So recall that t, this angle in radians, is s divided by t. Excuse me, t. I just said t is equal to s divided by r. S divided by r. I remember that, bless you. I remember it like, it's almost like slope, rise over run. It's just that the rise is an arced rise. You're going up around the circle, so it's rise over run essentially. Do you see why we call radians unitless? Radian is not really a unit. When you say something's in radians, you mean it's not in degrees. So S, units of length, correct? We're just measuring along the edge of the circle. R, units of length, so they cancel. So when you say the measurement is in radians, you're giving a pure number. There's no units to that number. It's just a number. So that is the area of a sector. 1/2 theta r squared if you had a theta. We are using a t instead of a theta, so it's tr squared. That's the area of that sector. If you plug in r value of 1, because it's a unit circle, t and s are the same. So the angle and the arc are the same, which is often why they call those things arc functions. because you're finding the arc, which is the same as finding the angle. So when r is 1, angle and arc are equal. Now, if you just, there's no reason to sort of do this for any practical reason, but if you did take this equation here, you plug in the r equals 1, and you isolate t, you're going to get that the angle is always twice the area of the sector there on a unit circle. You never did that in trig. You didn't do it in Calc 1, but I'm just telling you now that that angle is always twice the area, okay, on a unit circle. That is sort of the linchpin on how the hyperbolics and the circulars are connected. Again, you don't need to know, you don't need to memorize this. There's not specific questions that are going to be based on this. All right, so now we come down here to the unit hyperbola. We're going to call the ordered pair cosh and sinh instead of on a unit circle where you call it cosine and sine. We're going to call it cosh and sinh. And the connection is that this hyperbolic sector will have an area that satisfies this equation. The hyperbolic angle, it's not really an angle, but a lot of times we refer to it as a hyperbolic angle. So, when we're thinking about a circular function, the t or the theta is definitely a regular angle. It's a rotation. Often that is referred to as a hyperbolic angle, even though it's not really an angle. So it will be equal to 2a, just like in the circular function. So that is the connection. And other than that, and we don't use that connection a lot. That's just a justification for why we call these what we call them, because they have this connection. So definitions. These are important. You do not need to memorize them. In this class, we don't care so much what these convert to. But it's fascinating that these do convert to exponential functions. All right? I'm not going to ask you to convert to exponential functions. Some of the homework does ask you to convert. You can use your notes for your homework, so it's no big deal, but I won't ask you this on a test. Now, you've never thought of the trig functions as connected to exponential functions, but if the trig functions are related to the hyperbolic functions and the hyperbolic functions are related to the exponential functions, there is a connection between the trig functions and the exponentials, which we will see in this class. The most important hyperbolic trig function is cosh. That function is called the catenary. I've got a video in the video series that talks about the catenary. It was an outline problem for many years to figure out the mathematical equation of a hanging cable or a catenary. Like catenary, root word is cat, so lazy cat. Somehow they came up with that to call the curve catenary. Not a Maine Coon, just a regular cat. Not one of those weird cats from Maine. So cosh, you can think of it as the hanging cable function or the catenary. So it took a long time. When they were trying to figure out what the mathematical equation was, a hanging cable looks a lot like a parabola, but it's not. There is no parabolic coefficients that you can put in to make it a parabola. It looks a little bit like a lot of functions, and it's none of them except that. The hyperbolic cosine is the hanging cable. Now, when you think about this, the way I think about it is that if you busted this apart into e to the x over 2 plus e to the negative x over 2, e to the x is exponential growth. E to the negative x is exponential decay. So you can think about this as the average of exponential growth and decay. That's what the hyperbolic cosine is. It's the average of growth and decay. So if you think about just that, that's growth, that's decay, you're averaging them.
Let me guess the sine hx, that's almost the opposite where it goes up instead of down?
So it's the average of the difference. So it's going to go, yeah. Now the catenary, look, the next page will show you pictures.
Okay.
Before I show you the picture though, let's just look at these connections. It becomes, like when you start to look at these fractions, you say, oh yeah, this reminds me of the circular functions. The hyperbolic tangent, which I'll call tanh, is the hyperbolic sine over the hyperbolic cosine, just like tangent is sine over cosine. Tanh is sinh over cosh.
Is hyperbolic tangent and cotangent supposed to be the same thing as tanh?
This should be, yep, thank you. I will fix that error. That should be hyperbolic cotangent. Thank you. That should be hyperbolic cotangent. So tanh will be sinh over cosh. Cotang, so tanh and cotang, sinh and cosinh, cosh and sech. So it's how usually they're pronounced. So hyperbolic cotangent or cotang will be cosh over sinh. And so all these things sort of parallel what you've seen with the circular functions. Okay, so next page. Here's what they look like. Oh, no, not yet. Sorry. Next page is more connections. Again, things we don't have to memorize yet. This is just sort of really underscoring the symmetry or the analogs between the two. So with the circular functions, your primary Pythagorean is sine squared plus cosine squared is 1. Comes from the unit circle. Here, your primary Pythagorean comes from the unit hyperbola. You get cos squared minus sin squared is 1. And so then the question is, well, how do you remember which one comes first? With the circulars, it doesn't matter. Sine squared plus cosine squared or cosine squared plus sine squared. For the hyperbolics, it does matter. Cosh has to come first. Cosh squared minus sin squared is 1. Once we see the graphs, you'll see, oh yeah, cosh has to come first in order for this to be positive. The graph of cosh will be above the graph of sinh. And these other identities, you would get them the same way you got the other identities with the circulars. If you divide everything here by cosh squared, you'll get this one. If you divide everything here by sinh squared, you'll get that one. So those are the two alternative Pythagoreans. Odd-even properties are the same. Cosine is an even function, just like cosh is an even function. Remember, it's even if you put in the opposite of x and you get the same thing that you would get without the minus, then it's even. If you put in the opposite of x and you get out -1, multiplied by it, it's reflective, and so you get that symmetry. So that's an odd function. They call it symmetry about the origin. And so just like sine and tangent are odd, sinh and tanh are both odd. These formulas look really similar. There's a slight difference, but they're very similar. Again, you don't have to memorize any of these types of formulas. Here are the most important two formulas when we're talking about integration. With sine squared and cosine squared, in order to integrate those two, we saw one example already, a couple examples already. You have to power reduce. Same with the hyperbolic cosine and sine. If you have a square, you have to power reduce using these. They look very similar to the ones for trig. The ones are just on the opposite sides, right? Instead of a trailing one, the ones would be leading. For sine squared, you have 1 minus cosine of 2x. So it's just a slight reflective thing. But again, you do not have to memorize those. All right, finally the graphs. So there's the hyperbolic cosine, the hanging cable, cosh. There it is, just sitting there. It's up there at 1. So hanging cable. It's the average of the exponential decay function I have here and the exponential growth function I have there. Those are asymptotes for it. And then the hyperbolic sine, or the sinh, also asymptotically approaches the hyperbolic cosine when you're up in quadrant 1. Sinh looks a lot like a tangent function, except that there's no vertical asymptotes. It splays out, forever, both directions. So that's what they look like. So hyperbolic cosine is the one that you will see way more than hyperbolic sine. So the asymptotes for the cosh, the asymptotes for the sinh. Yeah, you can look at that carefully as you want. Now we're to what we need to understand. Derivatives and integrals for the hyperbolics. They don't show up a ton. They show up in certain engineering applications, depending. There's places where they show up. So it's the derivatives and the integrals. That's really the main focus for us, is just to know how to differentiate and integrate them when they do show up. Now you will get to some physics classes where they want to convert back to exponentials, or engineering classes where you want to get these in their exponential form. But for us, we don't care about that. We just want to get these derivatives down and integrals. So over here I have the ones that you should have memorized by now, the trig functions. Here are the hyperbolics. Almost the same. I'll underscore the two that are different are right there. The nice thing about the hyperbolics is that sinh and cosh are each other's derivatives. So you don't have to remember a minus sign there. Like you did when you're differentiating cosine, you get minus sign. Okay. So the one big difference, again, is the derivative of cosh has no minus, like we have there. But that leads to, okay, if that's minus, then this is positive. If this is not minus, then that's minus. So in my mind, the way I remember the signs here is that the primary three functions, if you're talking about trig, sine, cosine, tangent, those are the primary threes. For hyperbolics, the primary threes are sinh, cosh, and tanh. They're all positive derivatives. So you just have to remember then that the three other hyperbolics, all of them are negative. Namely sech. That's the easiest one to blow, because we're so good at differentiating secant and getting sec tan, and we just kind of automatically write it down. We just have to remember that it looks a lot like sec tan, sech tanh, but there's a minus. And then, of course, we have the complementary integration formulas. You know, if you integrate their derivatives, you get back to the functions. So that is the big slide. That is the slide that you want to focus on. This is the one that you'll be asked about on the exam if you look at the prior exams. So remember, I have both the prior exams from the last 2 semesters up there on OneNote. So you can look at the types of problems that are coming from this section. Nothing complicated, basic derivatives and integrals. So let's do some. So here are the integrals of the pure hyperbolic functions. Again, sinh and cosh are each other's derivatives, so they're also each other's integrals. If we integrate tanh, we first use our reciprocal identity, sinh over cosh, and it's in log form. Remember log form, if the derivative of the denominator is the numerator, you get the natural log of the absolute value of the denominator. Why don't I have absolute value bars around cosh? Cosh is a hanging cable. It's always positive, right? It's up above the x-axis. So we don't actually need the absolute value bars there. When we look at down here at cotang, it's also in log form, right? Because the sinh and cosh are each other's derivatives. Here we need the absolute values because that sinh function does pass down and get negative down in quadrant 4, or 3, quadrant 3. These two are wackadoodle. You do not need to memorize those. The other 4 you will see enough. And if you see them, this is how you should do your work. You need to show that you understand that this is log form. Don't just write from here to here. Just put this intermediate step in there so I know that you know that it's a fraction and that it's in log form. And like I've done in the past, if you were trying to indicate log form, you can just put in LF here. You don't even have to do it, but if you want to be extra particular, do that. Then I know you know that it's in log form, so you get the natural log of the absolute value of the denominator. Okay, all of that stuff. And now, finally, we get to do a problem. So, just like you did in calculus, in calculus you figured out the derivative of sine and cosine with limits. And then once you had those derivatives, you use those to find all the others. And so we're just going to start knowing those two derivatives. We know derivative of sinh is cosh and derivative of cosh is sinh. So that's going to be given. We want to find the derivative of sech. And so this is sort of a replay of what you did in Calc 1. If you want to find the derivative of sech, you're just going to convert this with a reciprocal identity. Sech is 1 over cosh, just like secant is 1 over cosine. And then what formula do we use for that derivative? Derivative of a quotient will be done using the quotient rule. Shocking. So you have to remember your quotient rule. I use the thing low d high minus id low over low squared. Different teachers teach it different ways, whatever your method is. So the low function is the one in the denominator, so there's low. What is d high? In other words, the derivative of the numerator. 0. Mm-hmm. So low d high minus high d low. High is just 1. And d low, derivative of cosh, sinh. Mm-hmm. And then divided by low squared. So cosh squared of x. Looking in the numerator, we have cosh times 0, which is, of course, 0. That's gone. And then what we do here in the numerator, we have minus sinh. And in the denominator, what we do is just break it into two coshes. We think of it as cosh x times cosh x. And in the numerator, I think of it as sinh x times 1. And then we can form two fractions. We can form that fraction, and we can form that fraction. So we end up with a minus sinh over cosh is tanh. So that's, and they write it in this order, so maybe I'll do this other one first. 1 divided by cosh is sech. 1 divided by cosh is hyperbolic secant. So sech. And then sinh over cosh is tanh. So that's how we would get to that derivative. All right, why don't we take our break and then we'll do the rest of these. We'll play around with some hyperbolics. Let me pause the recording. If you have questions, I can help you out during the break. Pause. We'll take a little bit of attendance. What are my duties? Anna Karina, you are here. Let's see. Cole. Richard. Hayden. Henry. We're down to 1 Henry. Daniel. Caleb. Moses. Harold. Sam.
Oh, because you can just.
Byam is here. Paul is here. Walter is here. Sean is here. Shelby is here. Connor is here. Jojo. is here. Oh, wait, no, I'm thinking integration. What am I talking about? Corbin. Maybe. Yeah.
Well, if we're doing the quotient rule, we're gonna start with
Zach.
We're going to do
Landon,
this,
back at the
that's
hospital.
derivative of the
Lincoln.
This is the derivative of the bottom.
Did it work out? Did it work out for anyone?
What's your answer?
You got somewhere. Okay, let's see if you got to the right place.
Squared.
Hopefully you're on track.
Which is the answer, but this is.
Yeah, you know the answer, right? All right, so cotangent. What direction is the fraction for cotangent? Sinh over cosh or cosh over sinh? Cosh over sinh. So we're taking the derivative with respect to x, cosh divided by sinh. So I find when doing the quotient rule, it's helpful to draw all the pieces. So I'll go low d high, so I'm thinking low is sinh. And then d high is also sinh. So low d high minus high d low. Oh, okay, cosh and cosh. Divided by low squared. Okay. So the numerator, we get sinh squared minus cosh squared. And what does that numerator equal? -1. So cosh, remember cosh is the hanging cable. That one's above sinh. Sinh is below it. So cosh squared minus sinh squared is 1. So if we reverse that, we're going to get -1. So this will be -1 divided by sinh squared of x. And 1 over sinh is cosec. So minus cosec squared x. That's what we're trying to get to. Cosec. Sec, cosec, tanh, cotanh. Sinh, cosinh? Sinh, cosh. I guess you could call cosh cosinh. Oh, the words. All right. I'm going to let you try the top one here. So chain rule, power rule, jammed in one. So practice your, this section is good at sort of practicing your basic derivative techniques with just some new functions. Practice your power rule, practice your chain rule. Gives you an opportunity to go back to your basic derivative techniques. Yeah, taking derivatives and integrals of hyperbolics, you start talking to yourself. Double chain. So the half is the first thing, half comes down. Subtract 1, that's the power rule part.
Oh, shit.
Whoa! Golly! What the hell? What are we, a pinnacle?
Cinch.
I mean, oh, yeah.
Oh, shucks!
Secant squared 3x. I forgot
Oh,
what it was.
oh yeah, that's the square.
What's that?
Is the chain rule?
That should be it. Okay, so this is what that's it. So it's 3
Struggle real?
Yeah.
pop, subtract, derivative of the inside.
Yes.
Because that's the derivative of less than.
That was probably the best thing. I was when it came to derivatives.
Once you're good at chain rule, that's a good thing because that chain rule is everywhere.
See how in my end,
How's this table doing with chain
multiply
rule?
by 3? It's because you take the derivative of the inside, which is 3, and multiply
How far do you just know?
Not too far.
Yeah.
So you should get
I mean, with trig functions and hyperbolic trig functions, you can keep going in circles.
Yeah. Yo, I saw that wrong. I thought that
Oh,
was
I know. I was
Oh.
just. Without,
Oh, that's okay. Never mind that.
Yeah, I know. When I looked at yours, it was like, wow, that was easier than I expected.
Okay.
All right, so let's go through this. The first step is bringing down the half. All right, so there's the power rule. Power rule, pop the exponent, divide, subtract 1. Now we multiply by the derivative of the inside, so that's a chain rule. And then we'll have to multiply again by the derivative of the inside of that, so we'll have a second chain rule. So the derivative of cotangent. So in my mind, I think, okay, let's go to cotangent. Derivative of cotangent is minus cosecant squared. And then we're just going to parallel that. So it's going to be minus cosec squared of the same angle. And then we multiply by the derivative of the angle and get 3. How's that looking? Everyone okay with that? And so the simplification here, we can combine the constants, of course. So minus 3, let's write this as cosec squared of 3x. And then down in the denominator, we're going to have 2 square root of cotangent 3x. And that is fine right there. You could start to get nutty and say, hey, if the question said convert to Sinches and Cosh's, you could go further. But if it doesn't say go to Sinches and Cosh's, you don't have to. So that's totally legit. Is that what you ended up with, River? Well, I saw some funny scribbling, and I thought, it can't be right. All right, how about this one? Try that one. What did you say first? You're having a blast? Yeah, so remember your derivative rule for a log. 1 over the guts times guts prime. Derivative, 1 over the inside, derivative inside. Yeah. That's derivative. For a log, 1 over the inside. 1 over the inside times the derivative of the inside. So 1 over sec times sec prime. So first part of the derivative for a log, 1 over the inside. And then in the numerator, we have to take the derivative of the inside. So here's where we want to remember that the hyperbolics have that pattern. The primary 3 have positive derivatives. The others have negative derivatives. So this derivative is not going to be just sec tangent. It's it's going to be negative sec tanh. And then we have a chain rule in there, so we'll end up with another 2 in front. And we'll have sec 2x, tanh 2x. This one we do want to simplify a little further because there's a routine cancellation. So we will end up with negative 2 tanh of 2x.
This might sound like a dumb question. These hyperbolic, what would you call them, identities?
I'm not sure. Identities.
Sech, cosh, and so forth.
Yep.
Do they act the same way as regular trig guide? Like,
Yeah, the identities are almost identical.
almost.
Yeah, almost. There's a couple little things that are different because the derivative of cosh is just sinh, whereas the derivative of cosine is negative sine. So there's those sign differences. That's it, though.
Okay.
Everything else is the same, but there's some sign differences.
So,
Other than that, they match nicely. Okay. Derivative of x tanh. Go for it. Got to get these Calc 1 skills primed. What rule are you going to use here? For x tanh? What's the derivative? What's the derivative of x? Is that what you said? Oh my gosh. Is it held the product?
No, I mean, isn't it just?
So what is the name of the rule we're using for that first one?
Quotient?
It's not a quotient. It's a product. Product rule. Product rule.
Okay.
Because we're multiplying those two functions together,
You
so we're
already know the tangent one,
using the product rule.
then you don't have to change it into the sine or cosine.
What's that? Yeah, product rule, if it's just multiplication, because there's no extra stuff inside the tangent, we don't have to do chain rule.
No, I was like, why is like spacing on it?
Yeah. It was last semester.
Sine g plus
Huh? Yeah, now you can have the product rule in place. Yes. So the product rule is interesting. And Zach, how did you say the product rule?
F prime g plus g prime n.
Is that how you said it?
That's how I said it.
That's how you said it, okay. And that does not matter in here. The one thing that's interesting about the product rule is that when you get to calculus 3, and you're doing the product rule when you have functions that are vectors, this works here. You could write this in lots of different ways. First derivative second plus second derivative first, or the way it's written there. In Calc 3, there's only one way to do the product rule when you're dealing with vector functions, because when you multiply vectors together, there is a type of multiplication called the cross product, and it is not commutative. So order is going to matter. So when I do the product rule, I'm always going to do it the way that you need to do it when you're taking a derivative of a cross product in Calc 3, just because you have to do it in that order. You can't just mix and match and make sure that you have one derivative of each and the non-derivative in the other position. So, but it doesn't matter here. Of course, it doesn't matter here because we have commutative law of multiplication, so the multiplication can happen in any order. It's not going to matter here. And commutative law of addition. So when I do it, I would say first derivative second. So first derivative of tanh is sech squared. So this is one of the primary threes. Primary three, sinh, cosh, tanh. Derivative's all positive. Derivative of tangent is secant squared, so this is going to be parallel and it's going to be positive. So first derivative second. And in Calc 3, your order has to be now, you have to stick in the same order. Now it has to be derivative first times second when you get into Calc 3. So here, of course, it doesn't matter, but I'll do it that way anyway. So derivative of first, what is happening? Derivative of first, does not like just that dot, I guess. Okay. Derivative of first times second. So tanh is next. Of course, we don't need that one. So simplified, there's not a lot we can do. So that's it. There's our derivative. Okay, super complicated looking one. This one has a combination of product rule, chain rule, power rule, all mashed together. Can you tell me what rule you're going to apply first?
Power reduction?
Product rule.
Product rule. Product rule is first. The primary operation here is that multiplication. We do not need power reduction because we are not integrating. When we have a cos squared or a sinh squared or a sine squared or a cosine squared, differentiating doesn't matter. You just do chain rule, pull the power down. But if you're integrating, that's when we have to use the power reduction rule. So for us, it's just, for derivatives, you don't have to do any reduction. But that is what's going to come first, is that product. And if it helps to label things first and second, of course you can do that. Any little tricks that help you are worthy? She flying? It's wrong. I looked carefully that time. It's the most common mistake with the power rule when you have a power on a trig function, and it happens because of the way they write it. Remember, note that cos squared of 3x is really the quantity cos of 3x. The chain rule part looks a little more obvious when you've written the base in parentheses. It's very easy to forget the derivative of the base because of that shorthand notation with the trig functions and hyperbolic trig functions. It's very easy to forget to take the derivative of the base. So derivative of second is our first real challenge. Say that again. So when we're differentiating cos, this is cos squared. So when we differentiate it, the 2 is going to come down. We're going to get 2 cos of 3x. But then we also have to differentiate cos. So there's going to be a little more, yeah. So here's how I'm going to talk myself through the derivative of cos squared. If you think of it this way, as cos 3x quantity squared, when you differentiate, the 2 comes down. You leave this alone and subtract 1, so you still need cos there. So it's going to be 2 cos 3x to the 1 power. So that's the power rule part. The 2 comes down, you leave the base, you subtract 1. Now what's the next step? Multiply by the derivative of the base. The derivative of cos, which is sinh 3x multiplied by 3. So that's derivative second, all that stuff. Is that okay with everyone? So power down, leave the base alone, subtract 1, derivative of base. So first derivative second plus the derivative of first is 2x. That one's easy, I guess, times the second. All right, so there's just a little bit of simplification here, not a whole lot. We just pull the 6 to the front. You're welcome. So that's going to be our derivative.
Would that be, do you need to factor stuff out, or is that fine?
No, factoring is fine. If we're asked to find zeros, we would certainly do that. But if we're not asked to find zeros, we'll just leave it expanded. Yeah. Because if we were trying to find zeros, what is the GCF of these two?
2x cosh.
Yeah, 2x cosh 3x. Yep. Yeah. Okay, so there's derivative. This is a good section just to help revisit all these rules. Now, the hard stuff, integration. Integration is always harder than differentiating. Okay. Anyone see, hint, use substitution? Anyone see what we should use for u? What was that? That will work. Walter?
The derivative of tanh is such squared.
That will also work. So there's two ways that are going to work perfectly. So if you choose such, that means the derivative of such has to be there. The derivative of such is minus such tanh. And if you let u be one of these suches, there is a such tanh that's left. So you can use such. You can also use tanh because the derivative of tanh is such squared, which is also present. So either one will work. Let's go ahead and use the such way. So if we let u be such, then du is minus such tanh times dx. So our u substitution will be, all right, we're only going to let u be one of these suches. All right, we're going to think of that such squared as such times such. And then the such tanh part is here. Such tanh dx will be minus du. So minus du. Let me write that as minus 1 in parentheses. And then no limits of integration. This is going to be minus u squared over 2 plus c. And then we'll do our back substitution. We'll have negative 1/2 such squared plus c. Now let's do it the other way. And just compare the two, because they will, antiderivatives for trig functions can look a little different. So if we let u be tanh of x, then du, derivative of tanh, such squared of x, times dx. So here, our integral, let's see, that's going to be du. It's just going to be u du. So we'll get u squared over 2 plus c, but our u is tanh. So we're going to get 1/2 tanh squared of x plus c. So this is equally valid. How do you get from one to the other? Pythagorean identity? right? Whenever you see trig functions or hyperbolic trig functions that are squared, you should be thinking Pythagorean. So if we go to our Pythagorean identities, we'll have a Pythagorean identity that relates sec squared and tan squared. And so you could get from one to the other if you use that identity. All right. Do this one in your head. In your head. It should take 3 seconds. Time's up.
Oh.
What form is it in?
Log form.
Log form. It's in log form. The derivative of the denominator, derivative of 1 is 0, derivative of cosh, sinh. So it's in log form. So this is natural log absolute value of the denominator plus c. Do we need the absolute value bars in this case? No, if you leave them in there, it's totally fine because it's correct. But you don't need them because the cosh is always positive. So the inside of this natural log is always positive. So you don't need the absolute value bars when something's always positive. All right, so that log form is a really good thing to be recognized. Always be looking out for. Derivative of denominator is numerator. Log form. Okay, top one here. Again, u substitution is pretty much all you have to go with. What do you want to let u equal? Cosec? That thing? Yeah, trying to sound out CSCH will give you a headache. So cosec. So if we think about cosec as u, one thing, keep in mind, we would never want to let u be one of the things squared. Because when you take the derivative of that, either cosec squared or cotangent squared, you would have to do the chain rule, and you get a long thing. Right? So we just want to let u be either cosec or cotangent if we're going to pick one or the other. So if we pick cosec, so if we let u be cosec, we would want its derivative to be present, or a multiple of its derivative. What's the derivative of cosec? Certainly it's negative. Cosec cotangent. Negative cosec cotangent. Times dx. And that is present. Right? There is a cosec cotangent up there. So that is present. So let's see if we can get to it. So if we put cosec in here, we don't want to do u squared here because we need one of the coseches to go with the cotangent, correct? So we're going to have, let me rewrite this as cotangent, cosec. All right, and then we'll just leave a cotangent. We'll just bust it all apart. Okay. So we have a cosec cotangent right there, and we have a cosec right there. What about that extra cotangent? Is that going to work? U is cosec, so we can let that be u. The derivative is cosec cotangent, so that can be that, but do we have, that thing's left over. That tells us that that's a bad choice for u. We only have two choices for u, either cosec or cotangent. That one's not working. This is how integration happens. It is not obvious which one to pick necessarily. All right, so let's try the other one. This is part of the process. This is part of the process you have to learn, maybe not to enjoy, but to endure. You must develop persistence All right, cosec doesn't work, so let's try cotang. And then let's see if we can figure out why we might have decided to choose that in the first place. What's derivative of cotang? Bang! So that takes care of that whole other thing, right? This is minus cosec squared. And so it's taking care of that whole other thing, which is why it's going to work. So when we go to do our substitution, we're going to let u be cotang. We can let u go to the 2 now. We don't need a cotang to come over here because of the derivative. So we're going to have u squared, and then we're going to multiply by, let's see, cosec squared dx is right there. That's minus du. So we're going to have a minus 1 multiplied by du. And that's swallowed up everything in there. Right? So the thing that is different here is that when we chose cotang, its derivative was this entire squared quantity, whereas when we chose cosec, we were only getting part of the other squared quantity. So we had part of the other squared quantity left over, which was our problem. And so, does everybody see that that's how the substitution will play out?
I don't understand what we did. Where
So-
did negative 1 come from?
So the derivative of cotang is negative cosec squared. So that's where the minus comes from.
Cool.
Now when we do our substitution, we're trying to match things. So when we look up here, we have cosec squared x dx. There's cosec squared x dx. So if we wanted to, we could rewrite this and divide by negative 1 here, so that the cosec squared dx, that part gets replaced with negative du.
Cool.
And so I'm putting it in parentheses because we don't want subtraction. It's multiplication.
Okay, and the u, could we have done u times cof as well, or does it have to just be a u squared? Like if you had made cof times cof.
Cotang times cotang?
Yeah, and
Then it would be
try
u
that.
times u.
It would be u times u. It would never be u times cot. Okay.
Yeah. So we have to turn all the functions up here. So if you think of this as cotang x times cotang x, you would end up, oh, why is there a dx there? There should be no dx there. The dx is after we take the derivative. So if we had cotang times cotang, we would have u times u.
Okay.
Right.
Okay.
So then we'll get minus u cubed over 3 plus c. And then we back substitute. All we have to do is look there. We're going to have a cotang cubed of x plus c. Bless you. Okay, last one here. This should remind us of what we did back in week 1, way back there, week 1. We were power reducing for sine and cosine squared. The identity looks very similar for sine squared. If we want to put it up here just as a reminder, what is the identity for sine squared? 1 minus cosine of 2x. So you can see the identity for sinh squared is almost identical. We just switched the 1 and the cosine 2x becomes a cos 2x, but you switch the order. Okay, so that's what we have to do, just like we did for trig functions. If we have a sinh squared or a cos squared, we have to power reduce. So integral of sinh squared is going to be integral of that. And when we do that, I'm going to just pull that half out to the front. That half is a division, that division by 2. So we're turning it into that. Division by 2 is a constant, factors to the front. All right, so we get 1/2 multiplied by integral of cos 2x. Sinh 2x over 2. Because we'll have to do a reverse chain rule. So the integral of cos is sinh with the same hyperbolic angle, but that angle is not just x, it's 2x, so we take its derivative and divide by that derivative. And then the integral of -1 is negative x. Then we have a plus c. Here, it's better to distribute the 1/2. Having a factorization for just part of an expansion is worthless. So the better answer by far would be to expand it. If you're going to factor, you want that factorization to come out of everything, not just 2 of the 3 terms. Any questions on either of those 2 thingamabobs?
I'm gonna be honest, I've been, this is all hieroglyphics after we
Oh.
got to,
I want to hear an explanation of that. Hieroglyphics.
yeah.
I don't think I've ever heard that word mentioned in Calc 2 in 30 years. Hieroglyphics. I don't even know what a hieroglyphic is.
After we got to the taking derivatives and integrals of the hyperbolic functions, I kind of need to go over what the,
Yeah, the relationships are.
Yeah.
I mean, the main thing with the derivatives and integrals, note cards is a good thing to do, is generate some note cards, because it's really, you have your 6 derivatives, your 6 integrals, and we're only doing 4 of the 6 integrals. We're not doing the integral of cosec or sec. Those are hard. So we're doing just 4 integrals and 6 derivatives. And then it's more the combination of power rule, product rule, quotient rule, and integration techniques. So that's where the hieroglyphics are coming in, is that there's probably mostly with the integration, because you have to remember all those rules, and integration's always a little harder. So I think with a little practice, if you stay after class, I can grill you and
yeah.
give you some extras. Okay, let's do a contrived application. So we want to find the volume interior to this inverted catenary kiln. So we have an upside down hyperbolic cosine. And that's it. Okay, we want to find the volume. So we need to find the area of the face and then multiply it by the depth. So here's our catenary that's upside down. We can use symmetry. So let's do that. So for our integral, we'll use this interval right there. If we use that interval, though, we need to know that point. So if we want to find that point right there, we need to set our curve equal to 0 to find the x-intercept. Okay? So if we come over here and we said 0 equal to 3 minus the cosh of x, we get cosh x equals 3. Is that a known x value? No. There's only one x value that we know for a hyperbolic cosine, and that's hyperbolic cosine of 0 is 1. So it's kind of like the natural log function, or log functions mostly in most log functions. You just know that one point generally. So hyperbolic cosine, hyperbolic sine, all we know is that one point. Hyperbolic cosine is 0, 1. Hyperbolic sine is 0, 0. So we don't know this. So all we can do is say that x is equal to the inverse cosh of 3. That's what that point is, inverse cosh of 3. That's all we can do. Cannot do anything else. Okay. So the area of our face, so first we'll find the area of the face. We're going to use 2 for symmetry. So that 2 right there is by symmetry. And then we're going to go 0 over to that number that we don't know. It's an irrational number. Inverse cosh of 3. And then we're going to integrate the function 3 minus cosh of x dx. That'll be the area beneath that inverted catenary. Okay, so antiderivative here, we're going to get 3x minus sinh. And that's going to go from 0 up to this strange irrational number, inverse cosh of 3. So if we plug and chug here, do you see that 0 is going to not contribute anything? 3 times 0 is 0. Sinh of 0 is 0. That's the one point on sinh that we know. It passes right through the origin. Looks a lot like tangent. Goes right through the origin. So we're going to end up with 2 multiplied by 3 inverse cosh of 3 minus sinh of inverse cosh of 3. So that is our approximate area. Oh, excuse me. That is our exact area. And if we type it into our calculator, we'll get an approximation. And now this question, it doesn't give us any real specifics, but we would have to use technology. If they said round it to 2 decimal places, we'd have to type that into our calculator. Volume is then area multiplied by the depth. And the depth is just 6 units long. So the volume will be 12 times this amount. So this is going to be the exact volume. And if we want an approximation to the volume, because they asked us for an approximation, all we would do is type this into our calculator and approximate to the decimal points that they asked us to.
Is there any way to do hyperbolic functions on?
Yes.
Yeah, there's like a little hypotenuse button.
Yeah, there's the hyperbolics are in that calculator somewhere in the function library. All right, any questions on how we navigate this where we don't have an exact value for that hyperbolic cosine? Does that make sense?
You're doing that on a TI-36.
Okay, well, that's the end of chapter 7 that we're going to do. That's it. So the focus for us, the 6 derivatives, the 4 integrals, that's our focus. None of the other stuff. So now I can start asking you some questions. Here's my first question. Ooh, that's so bright. Here is my first question. After I modify this page so that it's not blinding me. Let's see, view. Let's get it to be grayish. A little less painful. All right, here's my first question. Find the volume of the following solid object. So we're going to do a little bit of practice. I'm going to pick random questions out of thin air so we can kind of jump around. And a lot of times when you're trying to learn a new topic, you sort of learn it and you forget it, and then you learn it again, and that helps it sink in a little. So I'm going to just sort of bring up some functions, and we're going to do some things, and let's see if we can get you to think more conceptually about some of these ideas. So let's suppose we have this function right here. So that is going to be y equals negative x plus, nope, I want to make that a minus 1 squared plus 1. All right, so that's that function. And we're also going to think about the x-axis. So we're going to take this region, and I just want you to do the setup. I want you to rotate this around the y-axis and find the volume using shells. So find V using shells. I looped the setup. Just set it up. So start that. The shells, cylindrical shells. I'm going to fill my water while you remind yourself how to find a cylindrical shell.
Oh, my bad. The radius of the circle is 1.
Because if we're doing a y-axis, don't you want to do it in terms of y?
Like it goes out to 2.
Oh, okay, that makes
It's
sense.
right side.
So I think our limits are pretty sharp.
Yeah. No, I think it was. We're doing vertical guides, like vertical cylinders. And so I think it's from 0 to 2. Or at least that's like the radius.
Oh, yeah.
Yeah, I think 0 to 2 would be the.
So use the differentiating to X, which is.
Do you need
Yes,
to
I think it's
isolate X
just the function.
if you're using a shell?
Well, I was trying to find,
That x-intercept?
trying to find my boundary.
Oh, okay. So if you set y equal to 0, you should be able to do that.
Right, so 0.
Oh, you know those problems? Did I come up with that? Something's fishy. Yeah, your negative can't jump to the inside. Yeah, that's the issue. Yeah, something was fishy there.
Yeah.
Yeah, that minus, because it's a square, it can't jump to the middle.
What if you just set it up and it's supposed to be hard?
Does everybody see why we're doing it with shells and not washers?
Maybe just try to save time, but it's easy.
Does everybody see why? Does anyone have any question why we wouldn't choose shells?
Or wouldn't choose washers?
I mean, that. Why we would choose shells?
You would just choose washers.
If we tried to use a washer, we would draw an element this way, and then we would have to split the parabola into a right half and a left half.
And then also, when you try to isolate x, it has you take the square root of a negative.
Yeah, it would. There's probably more than one reason why it's a bad idea to try to use a washer there. So we're going to choose a vertical element as our strategy. And where is that vertical element? At what? at x. So any random vertical element is at a random x, so we call it x. And then what is the area of a shell? 2 pi rh, so 2 pi r is the circumference, and then h is the height, so that's going to give us our area of a shell. And do we want to turn the r and the h into x's or y's? We want to turn them into x's. We've chosen a vertical element. The thickness of that element is dx, so we need all the letters to match with the dx. So here we go. So 2 pi, maybe it's helpful to come over here and label what r is. R is the distance from the axis of rotation over to the element. That's your radius. And what is that? That is x. That is x. Okay. And then how about the height?
The equation.
Height is the function. It's the equation we have there for the curve. So that's going to be negative quantity, all that. So there's the area of our cylinder. Now the one other piece that we need are limits of integration, because when we turn this into volume, we have to integrate from left to right. I'm just going to drop this in. We don't need to do any simplification. We're just setting it up here. So we're going to integrate from 0 to, we need to know where this parabola touches down. So we would set this equal to 0. So if we come down here and set that equal to 0, what are we going to find that x-intercept to be? 2? Let's see. So here's the math. We would get x minus 1 is equal to, I guess we don't need parentheses anymore, plus or minus 1. So we're going to get x equals, if we go with the positive 1 first, we're going to get 2. Or if we go with the negative 1, we get 0. So those are the two intercepts here, 0 and 2. And so this is a 2. All right, any part of that you want to ask a question on? Okay, so that's cylindrical. Yep, 2 pi rh for the cylinder.
Yeah, so that's 2 pi over. That's right.
All right, next question.
So it is that easy.
Next question. Oh,
I don't want to do that.
I don't want to do that differently.
You're glad you act like you know you're doing it. You have to cheat because that equation doesn't cheat. Because you get -2.
Okay, next question. Find the work. Find work. Here is our vessel. We are going to do a cone. And we are going to empty the water out a little pipe that's 2 meters tall. We're just going to empty it right out of there. We are going to say that the radius of this is 3 meters. And we're going to say that the height of this cone is 10 meters. So find the work to empty that. Empty it out the, empty.
Is the radius 3 meters?
3 meters, yes. Water, yes. Not beer. All right, so work to empty that right out that pipe, so 2 meters above the top of the tank. So We want that acronym close at hand, ADD volume. When we're in 3 dimensions, it's ADD volume. When we're in 2 dimensions, it's ADD area.
Well, I think
Yes.
Okay.
Yes.
I'm just making
Yeah,
sure I'm
so take,
understanding
yeah,
that.
so the cone is filled with water, but when we pump it out, we're going to pump it 2 meters higher than the actual top.
Making sure I do that right.
Yeah, make sure you understand the scenario. You do not need the equation for the volume of a cone. No? I feel like I've been trying to beat that into your head. Oh, you were here that day? I'll try to beat it into your head today. So when we are finding, so we have the 2 scenarios, 3 dimensions and 2 dimensions. 3 dimensions we're finding work, and we have a little piece with that ADD volume. It's not the volume of the vessel, it's the volume of a slice. And so then today, where we have ADD area, it's not the area of the wall or the dam, it's the area of the strip. Yes. Yes. Area of that cross section is correct. Let's see. So first thing I see, we definitely want parentheses there. So let's just assume the parentheses are there. Squared unit minus.
Oh, I put the back in later.
Yeah, I had a feeling you might, because I know you know the 2 pi's just come into the front. So minus 2x, that's minus 2x squared plus 1 plus x.
Because I've been doing so much of the my math lab assignments, they don't let you put a CI in front.
Oh, right, they want it all jammed in there.
I'm used to jamming it in there.
Yeah. So then your x's are going to wipe each other out. Minus x squared. Yeah, that looks good.
I didn't know that we switched to the review, so I thought it was somehow gonna.
No.
Why is that useful, by the way?
The hyperbolics?
Yeah, because
Just because there's certain paths that objects like follow that are hyperbolic in nature.
Oh, it's just your.
Oh, yeah, like
the
the
light
light
you're saying.
Yeah.
It's just like that control.
It is the, yeah, and there's things like in orbit that gravity affects that will pull them into a hyperbolic orbit, not just a standard. So there's random places that hyperbolics come up. Not as much as trig functions, obviously, but they do come up from time to time. Okay, so here we go. We need to have a representative cross-section, so I'm going to draw that representative cross-section at a random y. We don't know the radius at this random y. So we're going to have to find that radius at the random y. In order to find that, we're imagining a coordinate system. So we're going to think of our coordinate system right there. We would need the equation of that right edge. The equation from here to here is y equals mx because it goes through the origin. Y-intercept is 0. What is the rise over run? 10 over 3. And then we have to isolate x, so x is going to be 3/10 times y. That is the radius of that disk. So the area of our of that disk right there is pi r squared, so that's going to be pi multiplied by that quantity squared. That's the area of that disk. Okay? And now let's go to our work. So work is the integral of ADD volume. So we have the 9.8. We have the 1,000 because it's water. And now the distance that our representative cross-section travels is what? 12 minus y. 12 is this full distance to the top of that little pipe is 12. 12 minus y is going to be that complementary distance. So there is our second D. And now the volume part, again, is not the volume of the vessel. It's the volume of our cross-section here turned into a slice. which just means the area of the cross-section times dy. So the area of the cross-section is pi r squared, right before our very eyes, and then dy. So there is our setup. We have slices of water from 0 up to 10. Right? So the limits of integration always physically match where the water or the fluid is, not up to the pipe, right? The height of the pipe is coming into that distance traveled by your cross-section.
The 12 minus y, is that did the 12 come from the 10 plus the
Yes.
2 pipe?
Yes, so this distance right here is 12. And so then 12 minus y. So that is our setup. So on Tuesday, we'll spend all day. I want to point out one thing. We'll spend all day reviewing. If you look at our review right here, we're going to go over all these, there's all these questions. We're not going to be able to go through all of them probably. There's quite a few there. But I did put a video solution in for every one of them. So if there's ones we don't get to, you have a video solution for it. So look those over ahead of time. If there's ones that you feel like, oh man, this one's super hard for me, maybe watch the video ahead of time or try it ahead of time or whatever. So
Where is this is this on the...
Does that make sense to everyone? I'll show you in one sec, Henry. So look at those review questions. Come in on Tuesday. We're just going to do problems all day and in preparation for the exam. All right, good luck finishing the worksheet tonight, and I will see you all Tuesday. Have a good weekend of math and whatever else you're doing.
We were just setting up that last one, I think, right?
Yes, we just set that one up.